So continuing on this, complementary events. So like I was saying, so the opposite of the event occurring. You've got to keep that in mind. And the trick to it is if you ever see the word not, or at least once, that's probably the bigger one you're going to see in your HST style questions. You're thinking of this. So let me just quickly do a sample question. So if I said, find the probability of at least one head when flipping 3 coins, right? So the trick to it would be, okay, probability of at least one head is equal to 1 minus the probability of no heads at all. So you can either write no heads or you can write all tails. However you, I guess, think about it, it's both the same thing. So that would be 1 minus the probability of all tails, well, a half times a half times a half, right? 3 coins. And that would be 1 over 8, so the answer would be 7 over 8. Does that make sense? So keep that in mind. If it says at least once, you've got to straight away know it's directing you to this particular problem. Be careful with counting in extension 1 problems. It may not be so straightforward, so we'll look at those probably in about 2 weeks' time when we do cover the extension 1 perms and coms, and we'll do extension 1 probability as well. Okay, so advanced, good. All right, no questions, move on. Let's have a look at a question like this. 3 runners compete in a race. The probabilities that the 3 runners finish the race in under 10 seconds are a quarter, a sixth, and 2/5 respectively. What is the probability that at least one of the 3 runners will finish the race in under 10 seconds? And again, just so you guys get used to this is the HSC question, as always, question 10 of the multiple choice, which means it is the state ranking multiple choice question. So this is the hardest one they could have thought of. Let's have a read of it one more time to understand what's happening. So there are 3 runners competing in a race. The probabilities that the 3 runners will finish the race under 10 seconds are a quarter, a sixth, and 2/5 respectively. What is the probability that at least one of the 3 runners will finish the race? Remember the at least, so probability of at least one is equal to 1 minus the probability of none finishing the race. Do we get that? And then when you're going, okay, what's the probability of none finishing the race? Well, if the probability of this guy finishing was a quarter, so not finishing would be 3/4. Not finishing would be 5 out of 6. Not finishing would be 3 over 5, and then it's just a matter of plugging into your calculator, and voila. Does that make sense? All right. So I've got actually another question I can do like that for you guys, so you can have a look. I'm going to find it real quick, but we can find it. Yep, pretty much that one right there. Have a quick read. As part of their strategy to reduce road accidents, police are using 3 different independent methods to detect speeding motorists on a freeway. The probability that a speeding motorist will be detected by a highway patrol officer is a third. By a fixed camera is 3/4, and by a mobile radar unit is a half. So the probability that a speeding motorist will be detected is a third, 3/4, and a half. So calculate the probability that a speeding motorist will be detected. Well, the probability of a a speeding motorist to be detected, so probability of detection is equal to the whole probability of an event occurring, which is 1, minus the probability of them not being detected. Not detected. So this one did not say at least or not. That's why I want to probably do this question. And then, I mean, from that, you obviously can see the answer. So not being detected, so if they were speeding and they weren't detected by the highway patrol officer, that would be 2/3. If they weren't detected by the fixed camera either, that would be 1/4. If they weren't detected by the mobile radar unit, that's 1/2. And then whatever answer that gives you, I'll just quickly plug it in. So you can see very similar style question, and pretty much the exact same style of math. All right, 11 out of 12, 11 over 12. So that means the probability that a speeding motorist will be detected is pretty high, because there's a lot of I guess tools to be caught. All right. Any questions? Okay. Let's go back and have a look at a. That's all right. I mean, I'll make that point. The multiplication principle. So when we multiply, it only applies if the cases are independent. If they were dependent on each other, then it won't exactly work like this. So multiplying is independent events. Another way to think about independent events is when you've got an and. If it said, what is the probability of getting a head and a tail, you would say 1/2 times 1/2. If the question said, what's the probability of getting a head or a tail, you would say 1/2 plus 1/2. There's a 100% chance of getting a head or a tail if you're flipping a coin, and if you're flipping 2 coins, heads and tails would be 1/4. Or even if you're flipping 1 coin twice, still be 1/4. So you can think of it like that: independent and then dependent events. All good. All right, we'll be covering that soon. This is pretty straightforward. I'll let you look at it yourself. All right, we've got another question down here. A little bit different. 50 tagged fish were released into a dam known to contain fish. So 50 tagged fish were released into a dam known to contain fish. Later, a sample of 30 fish was netted from this dam, of which 8 were found to be tagged. So 8 out of the 30 that they caught were tagged. Estimate the total number of fish in the dam just prior to the sample of 30 being removed. So that doesn't sound so much like probability, right? But the logic is it's closer to me, it's closer to ratios than it is to probability. And all it is just that it's saying the ratio of 8 to 30, so 8 fish that you found were tagged out of a population of 30 must equal to, I guess, 50 tagged fish out of a population of X fish altogether. Do you guys understand my logic there? So 8 tagged over 30 population, 50 tagged over X population. And then, I mean, it's simple. Questions? No, so far so good. Okay. Another easy question. There was question 1, so of course it's easy. A batch of 800 items is examined. The probability that an item from this batch is defective is 0.02. How many items are defective? You're just going to multiply them, right? So 800 items, 0.02. There's 16 defective. I'm sure that's an easy one. All right. Invalid arguments, they apply everywhere, but I mean a basic case would be something like this. This mathematics class has 24 students. The probability at the end of year 12 that a student will be rank 1 in the class is 1 out of 24. Rank 1 out of 24. No, that's not true. The probability at the end of year 12 that a student will be rank 1 is 100%. So someone will get first, someone will get second, someone will get, so the way it's worded, you got to be careful. That's just 100%. The probability, it's like me saying this one here, what's the probability of me getting a head or a tail? It's 100%. You either get a head or a tail. There are 24 possible ranks, so which is within this class, which is correct, but why is each student equally likely to be ranked first? You know that, effort comes in, homework, hard work, luck. So there's a lot of factors, pretty much. So it's not just a 1 out of 24. So you got to be careful sometimes with questions like that. Not so much a worry for HSC or anything like that. You won't get questions like this that are meant to trick you out. So you don't really have to worry about this component so much. Okay. Then we get to representing our probabilities using pictures. So either tree diagrams or listing or drawing tables. So a basic one that you've seen for a very long time now is a die is thrown twice. Find the probability that the pair is a double and so on. So let's just quickly do this one. So we'll just draw a table. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then that the pair is a double. Of course, you know that with A, it's just going to be a 6 out of 36, which is 1 out of 6. To get at least one number that is a 4, that's like you saying 1 minus the probability of no 4s. But I think in a case like this, it won't really make a difference. But you could have done 1 minus the probability of no 4s, just so you know. But I don't think we'll need to, because it's almost the same amount of math as me just going to my little table here and going, okay, at least one number is a 4. Well, that would just be 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, or obviously 4, 1, 4, 2, 4, 3, 4, 5, 4, 6. You can't overlap. And then what's that? 3, and that's 6 and 5. So that should be 11. And let me know if I make mistakes as well, or if I miss something as I'm teaching. Okay, and then now both numbers are greater than 4. So for both numbers to be greater than 4, then that means it can't be a 4. It has to be a 5 and a 1. Sorry, both numbers have to be greater than 4. So it has to be 5 and a 5, or 5 and a 6, or 6 and a 5, or a 6 and a 6. So 5 and a 6, sorry, 5 and a 5, 5 and a 6, 6 and a 5, 6 and a 6. So here, 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 and here. So that should be 4 out of 36, and then you simplify. Both numbers are even. I think we get it. 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, 6, 2, 6, 4, 6, 6. That should be 3, 6, 9. 9 out of 36. The sum of the two numbers is 6. For the sum of the two numbers to be 6, that means it has to be a 1 and a 5. So I guess we'll use red. 1 and a 5, 4 and a 2, 3 and a 3, 2 and a 4, 5 and a 1. So that's 1, 2, 3, 4, 5. 5 out of 36, and the sum is at most 4. So that means 1 and a 1, 1 and a 2, 1 and a 3, 2 and a 1, 2 and a 2, and 3 and a 1. And that's it. 3, 4, 5, 6. 6 out of 36. So it's pretty straightforward. Obviously, you just got to learn when you see questions like that. Those are all listing or drawing your table. And then really, it's pretty straightforward. Okay, let's do another one. There's no questions. So this is question 16. Question 16 is the last question of the HSC. So again, you understand this is not going to be your your simple one like this. It's going to be the hardest one you'll probably get to. I guess let's have a read first. A game involves rolling 2 6-sided dice, followed by rolling a third 6-sided die. To win the game, the number rolled on the third die must lie between the 2 numbers rolled previously. For example, if the first 2 dice show 1 and 4, the game can only be won by rolling a 2 or 3 with the third die. Full stop. All right. I'm going to stop there. Don't read anything else. Just tell me if you first don't understand the game. So have a read of it again. Because the way you've got to always do your probability questions is almost, I guess, mimicking the game. You're going to actually play the game in your mind. And if you can play the game, then you understand what's happening. So anyone there that doesn't understand how this game is working, okay then. So if you understand how this game works, that means you understand that if I threw a 1 and a 1 in the first 2 dice, a 1 and a 1 means that I cannot move on to the third roll, which means that would be impossible for me to even win. If I get a 1 and a 2, again, there are no numbers between 1 and a 2, so therefore I'll never get to the third die, which means again it's impossible for me to win. So I says, what is the probability that a player has no chance of winning before rolling the third die? Because like I said, I got a 1 and a 1 or a 1 and a 2. So the best thing to do is draw a table, just so you can picture everything. There's your 1, 2, 3, 4, 5, 6. There's your 1, 2, 3, 4, 5, 6. And everything in red is pretty much me being impossible to win. So if I rolled a 1 and a 1, a 1 and a 2, a 2 and a 1, 2 and a 2, 2 and a 3, a 3 and a 3 and a 2, a 3, 3, 3, 4, 4, 3, 4, 4, 4, 5, 5, 4, 5, 5, 5, 6, and 6, 5, 6, 6. That becomes 16 out of 36. The answer is 4 over 9. Do we understand that? So that wasn't too bad of a question if you understood the game. Yep, no problems there. Double A. A little bit trickier. What is the probability that a player wins the game? Can you guys tell me how you would win the game? Can someone tell me what are the ways you could win the game? Give me a sample of one, other than the example they gave. So how could you win the game? Anouk, give me an example of one.
If you roll 1 and 4 with the first two dice, and then you roll a 3 with the third one.
A 3 with the third one, or a 2 with the third one.
Yeah.
What's another example other than 1 and 4?
1 and 6.
Yeah, 1 and 6, and then now all of a sudden you've got 2, 3, 4, and 5. So you've got even a higher chance of winning. Yeah. Right? Okay, good. So, and then that keeps happening. Like if you did 2 and 4, you've only got 2 and 4. You've only got the 1 number in between. 2 and 4, you can only get a 3. But if you've got 2 and a 5, then you've got a 3 and a 4 that you could win. Or if you've got 2 and a 6, you could get 3, 4, and 5. Do we all understand that? That there's going to be a lot of cases So this is what I did for you guys. What is the probability that a player wins the game? What did I write? To win the game, the first two dice must be 1 and 3, or 1 and 4, or 1 and 5, 1 and 6, or 2 and 4, 2 and 5, 2 and 6, or 3 and 1, 3 and 5, 3 and 6, and so on, right? So, for cases where there's only one number in between, i.e. 1 and 3, so 1 and 3, there's only one number in between, which is 2, or 3 and 1, there's one number in between you could win, which is 2. 2 and 4, there's only one number in between, which is a 3, and so on. So for all those cases, there will be 8 such cases, and they're in green. So 1, 2, 3, 4, 5, 6, 7, 8. All of these cases, there's only going to be one number in between such that you can actually win in the third die. For 2 numbers in between, there will be 6 cases. So for 4 and 1, you know that there's a number 2 and number 3 that you could win. So there will be 4 and 1, there will be 2 and 5. There's also 2 numbers. Between 6 and 3, there's 4 and 5 that you could win, and so on. And they're all in blue, and there's 6 cases. And then for 3 numbers in between, there are 4 cases. And for 4 numbers in between, there are 2 cases. There's either the 1 and 6 or 6 and 1. All right, I'll pause there. Does anyone have any questions at this stage? Do we understand how I broke that down? 8 cases, 6 cases, 4 cases, and 2 cases. Because what you've got to work out, for you to be able to win the game, you need to first pass the first 2 dice, right? You gotta get past stage 1, let's call it. Once you're past stage 1, then you got to work out stage 2. So stage 1, there are 8 cases where I'll have 1 number, 6 cases where I'll have 2 numbers, 4 cases where I'll have 3 numbers, and 2 cases where I'll have 4 numbers in between. And then I'll just do the math. So 8 cases out of 36 times, and then the next game I only have 1 number to win, so I need a 1 out of 6 chance, plus 6 cases out of 36 times, there are 2 numbers that I could win, so 2 out of 6, plus 4 cases out of 36 times, 3 numbers that I could win, 3 out of 6, plus I've got to get 2 out of 36, and then times 4 out of 6, and then plug all that into your calculator, you get 5 out of 27. All right, what do we think? So like I said, there's not really much new math to learn. It's more applying everything you know and learning, I guess, how to do probability like this in Year 11 and Year 12. So there is a little bit more thinking rather than doing that's applied in Year 11, Year 12 probability. So what do you reckon? Novak, does that make sense?
Yeah, it does, yeah.
Good. Has anyone actually done probability at school yet?
We started.
Just started? Probability, not discrete, right? Just
no, normal probability.
Yeah, good. All right, all good. And yep, done. All right. So if everyone's fine, we'll move on. The math, like I keep saying, the math is not new to you. I'm not doing anything crazy. You've just got to learn how to, when you read a question like that, how to play the game. And I think the best thing I always teach is just put yourself in the game. Imagine you are the person that's playing this game and tell yourself, okay, how would I win? I would only win if it was a 1 and a 3, or if it was a 1 and a 4, or if it was this. And then slowly you'll learn to organize things the way I have just done. And I mean, there's no better questions than doing HSC questions, right? So HSCs or trial papers, that's all you should be really doing when you start a topic, especially a topic like this. The textbook questions won't help you. All right. let's move on to tree diagrams. I think most of us know how to draw our tree diagrams. These are the events of, like, I think the best thing you want to remember with your tree diagrams is, first, that this is the first event, and this is the second event, and this would be the third event, and so on. That's the first thing you want to remember. And then the second part of that is, this is the probability of the event occurring, and then the probability of the event not occurring, let's say. So 2/3, so let's say winning or losing. The probability of winning is 1/3, the probability of losing is 2/3, the probability of winning is 1/3, probability of not winning is 2/3, winning. Sometimes it does decrease depending on questions. So like if I go, I could have won, and then if I won, I become even more confident. So therefore, the probability of me winning actually becomes, I don't know, 2/3. Whereas the probability of me losing obviously becomes 1/3 all of a sudden. So be careful. Sometimes, depending on the question, it won't necessarily mean that it's always the same probability in each event. All right. All right. Any questions, you guys? No, that makes sense. All right. Let's do this question. Has anyone played McRook before? Really interesting game. I do recommend it. Look into it. Xavier is playing a variation of chess called McRook Online. Each game is graded, and Xavier begins with 0.6 probability of winning and a 0.3 probability of losing. You know that doesn't add up to 1. So that means there's a 0.1 chance of a draw. At the end of each game, players receive points. If Xavier wins, he receives 5 points. If he loses, he receives 2 points. And a draw will result in Xavier receiving 3 points. What is the probability that Xavier's first game ends in a draw? That's easy, 0.1. In the next game, after grading has occurred, Xavier now has a 0.4 probability of winning and a 0.4 probability of losing. So, like I said, this is the case I was mentioning above. It does change sometimes, and you just got to take that into account. Find the probability that after 2 games, Xavier receives 10 points. Okay, so the way our tree diagram would be something like this, right? We've got the first game, you can win with 0.6, you could draw 0.1, you could lose 0.3. In the second game, he could win 0.4, he could lose 0.4, which means he will draw 0.2. He would, and then if he drew, he could still win 0.4, 0.2, 0.4, and so on. All right. Does that tree diagram make sense? And you wouldn't have drawn a table for that one, right? So like you can kind of distinguish between the two different questions. Am I going to draw a table? Am I listing, or am I drawing a tree diagram? And then when you're thinking in the next game, that word there, okay, that's a second event. So it's more like a tree diagram style question. Find the probability that after 2 games, Xavier receives 10 points. For him to receive 10 points, that means he must have, the only way is he has to win and then win again. So 10 points would be win-win. 0.6 times 0.4, 6 out of 25. Easy. Xavier receives 5 points or less. How would he get 5 points or less? What are the different cases? Tell me. In the 2 games, he's got to get 5 points or less. What are I think there's a few cases. So tell me, what would be one?
He has to win once.
If he wins once, that's already 5 points, and even if he loses, that becomes 7.
5 points.
Say it again.
Yeah, I just thought it was equal to 5 points. Never mind.
No. He's going to be playing 2 games. So then he can lose. He can lose the first one and lose the second one. He'll get 4 points. So that's one option. Lose. And then obviously it'll be lose and draw. So 2 plus 3. Or he could draw, which is 3 points, and then lose. And that's it. He can't even draw because that would be 6 points. So 5 points or less, lose, draw, lose, or lose, draw. And then that's it. 11 over 50. So all I did was went lose, plus, right? All means plus this and this. So 0.1 times 0.4. And then or plus 0.3 times 0.2. And then plug it all into your calculator. And yeah. Any questions? No, good. Good. All right. I might give you guys a few minutes, maybe just to have a quick read of this. You should be able to answer it. This is really straightforward. Have a read of it, draw your tree diagram, and let's see exactly if it matches with the one I would have. Okay, I think we get the question, right? For Jack to log onto a computer, must put the correct password. Unfortunately, they've forgotten, and he's going to take some guesses. And the probability of success is 2/5, which means the probability of failure or not being successful would be 3/5. Assume that the result of each attempt is independent of the result of any other attempt. A maximum of 3 attempts can be made. What is the probability that Jack does not log onto the computer? So I guess the way I would have drawn it would be something like this, roughly. So let's say success, not, and then not success, successful, not successful, successful, not successful, and so on. Right, you guys get the idea, I'm sure. And then what is the probability that Jack does not log on? That means not successful, and then not successful, and then again not successful, which would be 3 over 5 times 3 over 5 times 3 over 5, which is 27 over 125. Right? And then, anyone want me to explain that further? Calculate the probability that Jack logs onto the computer successfully. Again, if I was to think of these questions, I would be doing them like this. So the probability of you being successful, you can see there's so many cases. So you're not really going to go and work out all those cases. What you will do is go, okay, being successful is 1 minus the probability of not being successful. So 1 minus the probability of not being successful, which is part A, is 98 out of 125. And then last one, calculate the probability that Jack logs onto the computer successfully on the second or on the third attempt. That word means plus, and then express. All right, here we go. On the second or on the third. So if you're obviously successful on the second, if you're successful on the second, that means you should have been unsuccessful in the first, and then successful in the second. Or on the third attempt means not successful in the first, not successful in the second, but then successful on the third. So your math looks something like this. So not successful on the first, and then successful, or not successful, and then successful. Not successful times successful plus or, and then not successful squared plus times successful, and then should give you 48 over 125. All right, what do we think? Can you say these basic probability questions in your exams? All good? You can get full marks for them? They're going to be worth around 4 marks in your prelims. And they're always following very similar patterns. All right, all good? All right, a little bit harder. Again, have a read. I guess I started it for Jane. You can see my answer for Jane. Maybe draw what you would have done for Laura, and then think how this works. Again, play the game if you have to. I'll just leave it with you for a second. Okay, Novak, do you think you understand what the questions, or how you would, like, how would you be thinking about this bit here? Obviously, so what is it trying to say here? What is it probably that only one of the two girls will select at least one strawberry? What are you thinking? What are the things you know, or I don't know, whatever. Tell me what you're thinking.
So what is the probability that only one of the two girls will select at least one strawberry lolly for her bag?
Yeah. Only
So you
one.
would only, without replacement.
No, yeah, without replacement, of course.
Without
Yes.
replacement.
Yes. Well, what's one thing you know? You know at least one. Well, how are you going to do at least one strawberry?
Yeah.
How would you do those ones?
1 minus no strawberries at all.
Good. All right. No. No. Oh yes. Sorry. At least one minus probability of no strawberries. Correct. Okay, we agree with that. So at least you would have known how to do that bit there. The problem is it's saying that only one of the two girls will be getting to this situation.
Yeah.
So how does that work? And that's why that's a more advanced style question. The way it works, so we've got we've got Jane, and we've got, who is it, Laura. And I don't know, you guys probably would have drawn something similar to what I've got with Jane for Laura as well. Blah, 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 blah. It doesn't really matter. It's more important, this last bit here, where it's saying that only one. So it can't be either one of us. It can't be both of us. It can only be one of us. So that means what would have happened is that if it was Jane to get the strawberries, then what must Laura get? Novak, what must Laura get?
Lemons.
Only lemons.
Yeah.
Or what's the other way around?
The two girls as well.
Yeah, that's it. That's how it works. So see, once you understand the game, or if you play it, if you put yourself there and you're like, okay, if only one of us, then this has to happen, and this person. All right, let's have a look. This is what I've written. So that means Jay gets the strawberries, or at least one of the strawberries, right? Because there's a lot of cases. And then that means Laura gets all lemons. Or Laura gets the strawberries, and that means Jane gets all of the, what was it? What's H stand for? Honey lollies. So Jane gets all the honey lollies, which makes sense. And there's the math. Just what you got to remember is that at least bit meant 1 minus, so you would put that into your memory bank, and then the only one, you got to think about it the way we just said it. If that means Jane can be the only one getting the strawberries, this Laura has to get lemons. So 1 minus honey, so 3 over 8, 2 over 7, 1 over 6, because you're not replacing, times this girl's got to get lemon. Lemon 5 out of 9, 4 out of 8, 3 out of 7. Plus 1 minus all these lemons, which means Laura gets all the strawberries, or at least 1 strawberry, times, and then Jane has to get all of the honeys. So 3, 8, 2, 7, 1, 6. All right. What do you guys reckon? Does that one make sense? What is it? Probably that only one of the 2 girls. All right. Any questions? All right. Very good. Very good. That would be a high advanced question as well. It could even come into your Extension 1 exams. Okay. Mixed bag. So what we might do. So mixed bag is just, both tools to be used. What I might do, just before we get started on this, just to make sure, I'll go back to this booklet and do a few more exam questions on those ones. Make sure you guys are okay. All right. All right, try that one. Example 8. A 6-sided die is biased so that the number 3 occurs twice as often as any other number. The die is rolled once. Show the probability that an odd number occurs is 4 out of 7. All right, I'll let you think about that for a second. A 6-sided die is biased so that the number 3 occurs twice as often as any other number. Anybody got an idea? For I? All right, well, let's pick someone then. Lucas, can you help us out?
Well, I just pictured as if the number 3 occurs twice, it's like having 7 numbers.
That is exactly what I would have done. Yeah. So think of it something like this. It's still 6, I guess. It's still 6-sided, but the fact that it's a bit more biased means the way you can think of it is that there are 7. There's almost 7 numbers, and that these 3s occur twice as often, as you can see. So the probability of a 3 is 2 out of 7. Probability of a 1 would obviously be 1 out of 7, 1 out of 7, 1 out of 7, and you can see everything else pretty much adds up to 7, and that is exactly what I would have done. And yeah, obviously show that the probability that an odd number occurs, odd would be 1, 3, and 5, so that's 1 plus 2 plus 1, 1 out of 7, 2 out of 7 plus 1 out of 7. Probability of an odd. Good work. Double I. If the biased die is rolled twice, find the probability of the sum of the uppermost numbers being 6. Well, again, that's when you would have listed it, but I think we can avoid listing it. You guys know it should be 1, 5, 1, 5, let's say 2 4, 3 3, 4 2, and 5 1. So I think we should be able to just get that out. Find probably that of the sum of the uppermost numbers being 6. So yeah, that would be. What am I doing? I was onto something until I just forgot my train of thought. What was I trying to do here? What was I trying to do? 1 and 5. 1 and 5. That's one number. 2. Yeah, so that's 1. Oh, maybe we should list it. Oh. No, it's okay. So 1. This occurs. Should we list it? Where's red dice? Find the probability of the sum of the uppermost being number 6. Why do I not want to list them? I should be able to just see it like this. 1 out of 5. I've lost my train of thought. I don't want to list it. Alright. Anybody help me out? 1 out of 5, 1/5, 1/5, 1/5. 1 and 5. That's 1? No. Oh. No. Let me just list it then. Because I've lost where I was trying to do it there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. To get 6s, okay. Yeah, 1, 6, 4, 2, 3, 3, 4, 2, 5, 1. 1, 2, 3, 4. 4, 1, 2, 3, 4. But to get a 3, it is twice as likely. And to get a 3, it is twice as likely. So 3 and 3, that should be 4. That's where I was getting stuck on 36. Which is 8 on 36. Yes. Is it on 36? Isn't it on 1/5? It's biased. So let me think about this actually. 8 on 36. Because there's 36 cases still though, isn't there? 8 on 36. Two. 8 on 36 compared to what would be my other logic? My other logic would have been to get a 1 would be 1 out of 7, which makes a bit more sense. And to get a 1, so getting a 5 and a 1 would be 1 out of 7. Five and a 1. Get a 1 out of 7 and 1 out of 7. And then plus 1 out of 7 times 1 out of 7 squared times 4 plus 2 out of 7 squared. Getting a 3 and a 3. That would be my answer. It probably wouldn't be this, but let me double check it before I confirm it. We have a total of 6, 8 out of 49. Right, let's see if my answer adds up. 8 out of 49, so 1 out of 7 squared times 4 plus 2 on 7 squared. 8 out of 49. Alright, good. I haven't lost it. 8 out of 49. Okay, so unfortunately, I was trying to list it, and the problem with the list, because it's biased, you might get into some problems. But instead, I decided to draw up our table and then just see it a little bit more clearly. It's probably a bit easier. So if the bias die is rolled twice, find the probability of the sum of the uppermost numbers of the upper. So the sum of the uppermost numbers being 6. So that would be 5 and 1, 2 and 4, 3 and 3, 2 and 4, or 4 and 2, and then 5 and 1. What's the probability of getting a 5? That would be 1/7 times, what's the probability of getting a 1? 1/7 as well. So 1/7 times 1/7. And then 1/7 times 1/7. 1/7. Why did I square it? I'm losing my train of thoughts here. This is really bad. 1/7. 1/7 for 5. Yes, I picked the 5, 1/7. I picked the 1/7. Why did I square it? Two on 7 times 2/7. This one is 1/7 times 1/7. Why did I square this? Did I do that wrong? 1/7 times 1/7 times 4 plus 4/49. No, it's right. The squared was wrong. I don't know why I got the squared there. Alright, back to it. 1/7 times 1/7, or 1/7 squared, maybe is what I was trying to say. So 1/7 times 1/7 is for this probability, right? This is 1/49. And then I just times it by 4, because these 4 would all be 1/49. 1/49, 1/49, 1/49. This one here specifically, you know, occurs 2 out of 7 times. So the 3, there's a 2 out of 7 chance, and then this 3, there's also 2 out of 7 chance. And then that should give you 8 out of 49. Did I lose anyone as I was doing this? Should I do it again?
Yes, please.
Yeah, that's fine. So, double A. If the biased die is rolled twice, find the probability of the sum of the uppermost numbers being 6. Okay, so we've listed our possibilities that we could get with our first dice, which is 1, 2, 3, 4, 5, 6. Same thing here, 1, 2, 3, 4, 5, 6. They have to sum up being a maximum of 6, and that would be only through 1 and 5, and then 2 and 4, 3 and 3, 4 and 2, and 5 and 1. Now, what's the probability of getting a 5 and a 1? Well, the probability of getting a 5 and a 1, let's just write it. Why is this not moving? There it is. The probability of 5 and a 1 is equal to 1/7 times 1/7. What's the probability of getting a 4 and a 2? Well, it's also 1/7 times 1/7, which is 1/49. What's the probability of getting a 3 and a 3? Probability of a 3 and a 3 would be 2 out of 7, because the probability of a 3 is 2 bits, right? 2 bits out of 7. So the probability of a 3 would be 2 out of 7 times 2 out of 7. And that gives me, what, 4 out of 49? And then obviously you got 2 and 4, which is still going to be 1 out of 49, and you've got 1 and 5, which is also 1 out of 49. So all I did here was I worked out one of them, 1 out of 49, and then multiply them by 4, because I know these are the same probabilities, and then I added the extra 3. But otherwise you could break it up like this, and then you add it all up, gives you 8 out of 49. Does this make more sense now?
Yeah, it does.
Where are you stuck? If you're stuck on something.
Oh no, I was just stuck on how you worked it out. That was all.
But are you sure you get it now? Or not?
Yeah.
Just. Okay. 100. Are you sure?
Yeah, I'm sure.
Okay. All right. Done. All right, good work. And then what do we got? This biased die. Anyone else actually? Well, that makes sense. So 8 out of 49 is the answer we want for that one. 8 out of 49. This biased die is now rolled together with two six-sided dice. Okay. What is the probability that at least two odd numbers are uppermost? This biased die is now rolled together with two fair six-sided dice. Okay. So that at least two odd numbers are uppermost. At least two. All right. How would I do it? Triple I. Let me think about it. Probability of at least two odd. At least two odd. So it's this, and another one, and a third one. At least two odd would be 1 minus the probability of 0 odd and 1 odd. 0 odd and 1 odd. So let me just think. 1 minus the probability of even. Oh, there's so many cases. 2. Whoa, so many cases. Is there a faster way of doing this? Anything? 0, or at least two odds. Because there's going to be like what? There's 3 dice, right? We know there's 3 dice. 3 dice. At least 2 odds. So that means 2 odds. Oh, actually, that's probably faster to do 2 odds plus 3 evens. Sorry, 3 odds. What am I doing? 2 odds and 3 odds. It's probably faster to do that than to do this version. Because I can see to do 0, it's going to take a long time. So if there was 2 odds, 2 odds, 2 odds, 2 odds, 3 dice. That means, remember, and one's biased and the other 2 are normal. Normal, and let's call this one normal as well. So with the biased dice, look at the cases. There's 2 odds and 3 odds. Let's do the 3 odds. That's easier. For the biased one to be odd, the odd case we worked out was 4 out of 7. Right? So biased, 4. Maybe I probably won't be doing it this way. I think it's easier to just go and add your 2 different cases. So we'll do 3 odds. 3 dice. Okay, odds. So we're doing 3 odds first. 3 odds first, yeah. So which is 4 out of 7 for the bias case. For the normal dice, odd is half. For your normal dice, odd is half. Do we agree with that? And then for it to be 2 odds, remember it could have been even here, and then odd. It could have been odd here, even, odd, or it could have been odd here, and even here. So for 2 odds, there are 3 cases that we've got to consider. So the first case for even would be 3/7 times half times half. Then odd would be 4/7 times half times half. And then this should be 4/7 times half times half. And then if I'm not wrong, we plug all that into our calculator and we should get the answer we're looking for. While I do that, anyone have any questions? (15 over 28). unless I put something wrong in my calculator. Let's double check. Probability 15 on 28. Beautiful. And yeah, like you can see, there's no real other way of working it out. You have to break it up in terms of the different cases. If you wanted to do it this way, it would have been fine. Obviously, it would work out. It's just that I realized it's actually going to be a lot longer than the 4 cases that I just did here. So that's why I just decided not to do that, because it'll be obviously longer. So that's silly. All right, questions? Who's hating probability? No, fair enough. I absolutely hate it. I prefer calculus and algebra over this. Good news, pretty much 6 out of 7 of our topics in year 12 is all calculus and algebra based, so you won't be touching on this much. Next year. All right, but anyways, here we go. Nicole, again, I'll leave you to think about it for a little bit. This one should be easier the way I'm reading it. It could help if you know a bit of about tennis, but it doesn't matter. You don't need it. You just read it properly. All right. I'll let you think about it for a second. Nicole and Mariana play against each other in the 3rd round of the Australian Open. In this tournament, the first player to win 2 sets wins the match. The probability that Nicole wins any set is any set, so it doesn't decrease or increase, so she doesn't get more confident or anything like that, right? It's constant 70%. Well, this would be like a tree diagram style question, right? Because you got different events, the first event, second event, third event. So I hope you guys realize that. So it would look something like this. Win, lose. And then this would be 70%, and this would be 30%, let's say. And then same thing again. Win, lose. Win, lose. All right, let's see how this works. So find the probability that the game will last 2 sets only. Okay, how would it last 2 sets only? What needs to happen? What needs to happen? Come on. What do you guys think to do?
Someone has to win twice in a row.
Someone has to win twice in a row. So that means Nicole has to go win for Nicole, or Mariana will have to win. What's the probability of Mariana winning?
30%.
Right, because that's the probability of Nicole losing, of course. 0.7, which is 70% squared, times 0.7 plus 0.3 squared. That's your answer for I. So it's either Nicole will win, or you could think of it as Nicole losing, both of them, or in other words, Mariana winning, both of them. However you want to, I guess, do your math there. doesn't really make a difference. Good stuff. Double I. Find the probability that Nicole wins the match. Okay, how would that work for Nicole to win the match? So obviously we know it's win-win plus what? Novak, I think you're into tennis, so tell me. Win-win or no? Anybody else that knows what needs to happen?
Lose.
But then you didn't win. Mariana needs to win. Oh, sorry, Nicole needs to win. Sorry. Nicole needs to win. So if she loses...
Mariana 2 loses.
Say that again?
Mariana loses twice.
Yeah, but isn't that the same as Nicole winning twice?
Yeah.
Yeah.
Win, lose, win.
Yes, that one. Win, lose, win. I didn't draw it because obviously that would have given the answer. But what you got to understand, if Nicole wins, that's one set. Then she loses, that's only one set to one set. Then they've got to play a third game. Then she's got to win again. Good. And one more.
Lose, win, win.
That's it. Lose. You got to lose the first one, but then you'll win the next two. That would be the way it would work if you need to win 2 sets. And then, of course, 0.7 times 0.7 plus 0.7 times 0.3 times 0.7 plus 0.3 times 0.7, 0.7. You can put squared, whatever. And then that should give you the answer we're looking for that one. And then, of course, find the probability that Mariana wins the match. How would you work that out in pretty much one line? The probability that Mariana wins the line. Or wins the match, sorry.
Same thing, but switch the 0.7.
You could. Good job. Yes. You see it logically. Fantastic. But give me an...
Complementary.
Yes. Beautiful. Why wouldn't you just go 1 minus the probability of Nicole winning the match? Right, enough? Makes sense, doesn't it? So Mariana winning, 1 minus Nicole winning, and you just worked out what probability of Nicole winning is. So it'll just be a little bit faster. And that's why it's worth 1 mark, right? I mean, that's what you're going to look at. When you're starting to look at your exam style questions, you look at, oh, it's only a mark. But yeah, it's also there because you could have just copied the same thing and just changed your 0.7s to 0.3s, your 0.3s to 0.7s, and yeah, good stuff. It wasn't too bad. All right, how are we going for time? All right, I might stop that one there.